Hi guys, welcome back to Biology Videos at TDA, OCR 13.5. We're going to look at synapses and neurotransmitters. We're going to recap last lesson a little bit because there's quite a lot of learning from the last couple of lessons of just physically learning and memorising things. Okay, so let's have a look. So we're going to recap action potentials to start with. It's so important that we learn it. So a reminder of action potentials and resting potential. So here we've got the image from a resting potential. A couple of key points to remember. We've got the 3:2 sodium ATPase pump. So we pump 3 sodiums out for every 2 potassiums in. And the membrane is more permeable to potassium. So therefore more potassium is going to leak out. And the sodium is going to leak in. And then finally you have these negative proteins that keep the inside negatives, which leaves us with an overall of around minus 70 millivolts inside. Okay, so that's our resting potential. And then our action potential, reminder of how we do that and different parts of the graph. So number 1 at rest, we're at minus 70. When some kind of stimulus is applied, we are now depolarized. So from step 2 to 3, we are depolarizing because we were polarised, and that's going to go to about plus 30, plus 35, plus 40, depends where it's quite around there. So that's when the sodium channels are open, so sodium rushes in. Then they're going to close, potassium channels are going to open, and then potassiums are going to diffuse outwards. That's going to then lead to a repolarisation, and then it hyperpolarises because they stay open for a bit too long, and then it turns out as rest again. Okay, so we're going to look at synapses in this lesson. So first of all, what is a synapse? So synapse is the gap between and the pre and post synaptic knobs. It's the whole thing between neurons. It's the gap and it's the transmission from one to the other. And it's the way in which information is sent between them. And it's controlled in a variety of ways. The two we'll learn about more in the next lesson is temporal and spatial summation. But we'll get to that a little bit more. So the interesting thing about neurotransmitters and synapses is it's not the simple case of you just simply pass on a message. There is regulation at those synapses to control the message. You can increase the frequency, decrease the frequency, and various other things. But we'll look at the control a little bit more. First of all, we're going to learn the process itself. So you've got a pretty typical sort of diagram of a synapse, and you've got your presynaptic neuron at the top, and then your postsynaptic neuron at the bottom. So it's just the difference in the prefix of the word. And then you've got some calcium channels, you've got some vesicles, you've got some mitochondria, and then some endoplasmic reticulum that you should kind of recognise. And then on the postsynaptic neuron, you've got some receptors. So let's have a look. The synaptic cleft is the gap between them. We've got our calcium channels there, we're all labelled up. There's the postsynaptic membrane, the sodium channels, and these are sodium channels because once we have bound the neurotransmitter, the receptor to the sodium channels, that's going to eventually cause the beginning of the next action potential, which is started again by sodium rushing in. We've got these vesicles with neurotransmitters. They can change. The example we're going to use is acetylcholine, but there's a few different types of neurotransmitters. You'll have heard of some before anyway. Okay, so we've got our action potential that's coming in. We're going to pass on this message to make a new action potential. So we're going to look at this process. So step 1, kind of notes now if you want to make notes. Your step 1 is once this action potential reaches the synaptic knob, what's going to happen is the first step is calcium channels are going to open. They'll be voltage gated calcium channels. So they're going to open. So extracellular calcium, so in the extracellular fluid, calcium then is going to flood into the synaptic knob. Okay, so the channel's open, and then calcium ions are going to then flood inwards. Okay, and they'll close again. So that's the first step that's going to happen. The second one, so they will essentially bind to some receptors on the vesicles. That will cause the vesicles to fuse with the presynaptic membrane, and we'll have exocytosis. So we're going to release now the neurotransmitter across the cleft. So calcium channels open, calcium channels flood in. This causes the vesicles containing the neurotransmitter to fuse with, and you see the best animation you've ever seen. There you go. Fuse with the postsynaptic, the presynaptic knob membrane, and that's going to cause the release of the neurotransmitter. So next thing, step 3. The neurotransmitter is going to be released across the cleft and that's going to bind to the receptors on the postsynaptic neuron. So they're going to diffuse by normal diffusion, and they're going to eventually bind to the receptors on the postsynaptic neuron, which is normally going to cause the sodium channels to open. So they're going to open, and then the sodium ions are going to then flood inwards, and that's going to cause a depolarization that we've learned from the action potential. There we've got some empty vesicles, and then what we also have now is a load of neurotransmitter that needs to be done with them. So sodium channels have gone in, we're depolarized. Okay, so that's step 3. That was still combined with the other step 3 notes I put before. Step 4, we've now got this new action potential that's causing the depolarization. So the next action potential to occur down the next neuron. So we've reached that threshold of about minus 55 millivolts, and that's going to cause this excitation. Okay, so there's one more thing we need to go into. We'll come back to that in a second. So what we've got left over now is this acetylcholine. So one of the neurotransmitters which is really common is acetylcholine. Okay, now if you've got too much acetylcholine, I'll show you in a second, that's going to cause continuous depolarization, or it's going to keep the sodium channels open, so it's going to mess up the action potential on the postsynaptic neuron. So what you have to be able to do is to break it down. So we use an enzyme called acetylcholinesterase, and if you break the word down, so it's acetyl choline esterase. Okay, it's a hydrolytic enzyme, and it's going to break down acetylcholine into acetyl and choline, which is ethanoic acids for the chemists. Okay, but we can refer to it as acetyl and choline, and that will break it down, and they then don't cause this change of shape on the sodium proteins channels, and that doesn't then cause the sodium to go in, so we can regulate this. So the enzyme's going to come along, and that's going to break apart the acetyl and the choline into its separate parts. Okay, this is then going to cause the sodium channels to close, and then they're going to then diffuse, the acetyl and the choline are going to diffuse back across the cleft by normal diffusion, and then we can recycle them, so we can reuse them, otherwise we've used it up. Sodium's gone in. Now we're going to break down the acetylcholine, or the acetylcholinesterase. Now, why do we do it? So a couple of key points to put down there. If it's not broken down, it will continuously generate new action potentials. That's your kind of key point there. So, how we remake it. So we've got to remake it. So you'll have noticed there's mitochondria in the presynaptic knob. So ATP is going to then be released by that, and that's going to cause the acetyl and the choline to recombine together. And then they can then be restored in synaptic vesicles. And we can make some more in the smooth endoplasmic reticulum there. And this can then keep going over. We can keep redoing this cycle over and over again. Okay, so I'm going to slow down on the exam questions. I'm going to save them up, and I'm going to ask in future lessons for you to do some, and send me pictures of them, and then I'll mark some. But here's some questions, you can have a go at them. You can pause the video. Okay, so the hydrolytic enzyme is acetylcholinesterase. Why must it be broken down? Because it will cause continuous action potentials. What happens to the remnants? They're recycled and they're repackaged into acetylcholine again. So I've got the whole process, which I'll summarise now. Sorry, excuse me. So, incoming action potential comes on in. Calcium channels open. Calcium ions diffuse inwards. This then causes vesicles containing neurotransmitter to fuse with the presynaptic cleft, presynaptic neuron across the cleft. Neurotransmitter goes across the cleft by diffusion, binds to receptors on the sodium channels on the postsynaptic neuron. This causes an influx of sodium ions, creating a new action potential. Then the neurotransmitter acetylcholine is broken down by acetylcholinesterase, which is going to then be recycled. Okay, so the kind of only task I want you to practice, and I don't mind how you do this, I don't mind if you create some flashcards, if you ask someone in your house to quiz you, if you watch some more YouTube videos online, if you Google YouTube, synaptic transmission on YouTube, you'll find loads of videos on this. So I want you to summarise these three things. So resting potential actuators and synaptic transmission. And I want you to create some kind of log. So you should be at a point where you can, off by heart, talk them through. So rather than me set you lots of exam questions, I'd rather you spend some time now and practicing these. So you should get to a point at the end of this lesson that you can do that for these three things. There is more in the Caboodle textbook on synaptic transmission, so don't worry, I haven't forgotten. I will go through it more in next lesson. But that's what I want you to do for the rest of your time for this lesson. Okay, you can submit via a photo as the normal way. I'll set it for Monday now because we've got a bank holiday weekend to give you a little bit longer. Thanks very much, guys. Have a nice week.